Hi, my name is Stanley Bishop, and I am head of data science for a company called Drift Biotechnologies. I'm here to talk to you today about machine learning and microbiology in the cloud through Ray. I'm so excited to talk to you guys. Uh, just a little bit about my background as a data scientist, because I feel like um, Ray is more than anything really a tool by data scientists and for data scientists. And some of the core challenges in my career as a data scientist are really, I think, reflected in the feature set of Ray. So I'm really excited to talk about that. Um, I started off really wanting to be a mathematician. And I remember my first year of school, a lot of people in my family said to me, what kind of job are you going to do with the mathematics degree? This was a different time. Um, it has been so interesting then, having had such an incredibly rich experience working with companies across many different spaces, doing mathematics as a data scientist. I've been lucky enough to work in problems of language translation, modeling 3D spaces for virtual reality, um, data systems for monitoring the health and optimizing the growth of biological systems for agriculture. Um, Obviously, like finance provides some of the most complex modeling problems, and I've done work in that space. And I'll tell you too, I love children, and I've been able to do some work on modeling the development of children through language and natural language processing. Um, and then last but not least, another aspect of my story as a mathematician who became a data scientist is that I had to leave research because of some negative health outcomes personally. And so, amidst this grand exploration of the space of data science, like medical technology and biotechnology have been one of my real North Stars. And so, I have been incredibly privileged to be working with a company called Drift Biotechnologies for the past year, and leading their charge on data science. Uh, the slide you can see here, I think presents perhaps a caricature of the story of Drift, but one that I hope will get the idea across. Starting with Spark, which is just such a powerful cluster technology for data systems. You have a company, Databricks, which took the complex open source tools reflected in Apache Sparks and created a integrated consumer platform that allowed people to scale companies more successfully. Um, Down the list, you have Twilio, which came into a space that was very fragmented with a large number of players transacting telecommunication data, and they created a unified suite of tools that didn't just streamline the usage of these traditional tools, but allowed entire new companies and concepts within an integrated ecosystem. And that is just the type of story Drift is trying to tell in the space of genomic analysis, specifically for microbiology, which we feel is an undercovered space. On the left side, you can see this absolute alphabet soup of open source sequencing frameworks. There are so many more, and we're looking to help bioinformaticians mostly forget about them. Um, why is genetic sequencing particularly interesting? I would share these two graphs. Genetic sequencing is undergoing revolution in scale of data. This is being driven by an accelerating sequence of engineering technologies for actually capturing the data stored within a sequence. And at the same time, computational technology driven by Moore's law, but exceeding Moore's law's rate of development, is reducing the cost of sequence analysis and assembly for this rapidly expanding ocean of genetic data that exists. So it sort of creates more and more demand for these tools. And as I was alluding to in the last slide, the sort of fractured ecosystem prevents greater and greater struggles for practitioners. Getting into some of the challenges facing this industry, I picked two pictures to illustrate the pain of bioinformatics. On the left side, we have a diagram of what I would describe as a typical um, sequencing topology for assembly process. You can see it's a multi-step process. Each step reflects computational nodes that could encompass very large RAM scales, very large numbers of compute nodes. There's a large number of checking and asynchronous processes. Uh, all of this traditionally has been done on hardware. These types of clusters are typically called Beowulf clusters, or utilized by large companies that are able to put together large scale capital budgets, and they can add a zero to allow them to not have to worry about the computational hardware. But it's not the most economical way of doing things, and it also, I would argue, limits a practitioner in their agility. And the real exciting thing, oh, I'm sorry, bioinformatics is so hard that I actually have a second slide that goes into some more details about why it's so hard. And bioinformatics is so hard in part because it requires the expertise of three different types of practitioners working in tight concert. And for each of these three types of practitioners, the complexity of the tasks that they're asked to contribute into bioinformatics workflows are at the extreme of the complexity. On the left-hand side, we have biologists who work with data scales that are extremely large, given the sequencing revolution I mentioned. They deal with very complex taxonomical relationships to even understand and discuss the organisms they study. And the selection of software is extremely fragmented. In microbiology specifically, the capital investment in laboratory space and the accumulation of domain expertise and labor capital is extremely challenging for people trying to start up labs. And also, obviously, a lot of this is happening under corporate umbrellas. And so there is a lot of research siloing, and it's often challenging for researchers to find out what other people in the space are doing. Quantum chemistry also has to be mentioned because increasingly projects like AlphaFold out of DeepMind are actually answering the question of what happens when DNA runs, like very specifically. And so people in very disparate fields of microbiology, from drug discovery to bacteriology and virology, are starting to ask questions about the actual particular complex interactions of geometric structures. And so that field is just a whole can of worms itself. In the middle, we have sort of some descriptions of challenges facing cloud engineers in this space. There's a lack of modern DevOps practices. A lot of the labs producing software in these pipelines are academic, and they don't have exactly the same experience someone coming from GCP or AWS would have. Additionally, the quality and availability of software packages is sporadic, to be described generously. A recent paper I read actually showed that research impact has no correlation with stability of software. And so there's some real questions to be asked about how engineers should be integrated with and contributing to bioinformatics projects. The database, the diversity of databases practitioners need to work with is extremely vast. The data is coming from public sources, private sources. The level of quality and schema curation is extremely variable. And then, of course, resource management. In contrast to the Beowulf clusters, cloud technologies for bioinformatics have the potential to really cut costs, but it isn't an easy lift. You have a lot of systems coming on, talking to each other, turning off, and the data has to end up in the right place. I, humbly am grateful to our engineers for what they need to deal with. And then finally, on the right side, we have, my bucket in terms of data science. And when it comes to bioinformatics, the diversity of algorithms is enormous, from the type of data we need to feed into the algorithms through featureization to the model selection, which ranges from, transformer models in some instances for proteins to very I'd say blood and guts linear algebra at scale. Um, and then hyperparameters are something where even some of the best algorithms doing classification and prediction of genomics are under optimized for hyperparameters. And it's largely because some of these fields are very new. For data sets, obviously the out of memory question is a big deal. For every data scientist who knows how to push to clusters, there's 10 who don't, and the 10 are typically less expensive per hour. So in these kind of projects where we need to rapidly prototype pipelines and test components, we really struggle having too few people who can run algorithms out of memory. And so this is just a good moment to tip my hat to Ray for making our job a lot easier. But that's getting ahead of ourselves at this. Just finishing out this slide. Analysis itself is very challenging. Communicating and representing results of data science processes back to the other domain experts in biology and engineering presents great challenges. What does this all look like in practice at a company? Big academic fan of the idea of operational loops for understanding operational health in companies or organizations. This would be a representation of our workflows at Drift. I work in tight coordination with an extremely talented VP of engineering and an extremely brilliant and qualified biologist who's a bit of an expert. And every day I am both communicating complex data science concepts to my counterparties, absorbing complex engineering specs, synthesizing the engineering spec, communicating it to biologists, receiving spec from the biologists, translating spec to the engineers. I would say that for complex interactions between highly skilled professionals, it's the most challenging project and the most rewarding project I've ever been involved in. But the real sort of motivational imperative for the whole process has been tightening these loops, tightening communication, and the real solution space, I'm not going to surprise anybody by sharing, has been Jupyter Lab. Jupyter Lab is the centralizing element for our operational loops. Jupyter Lab allows each practitioner to have a common interface to the company's entire data system and project structure. It allows each user's experience to be understood and curated, and data to be taken about the workflows through the Jupyter Lab interface. As a further example, we have an illustration of some of the systems we orchestrate through the Jupyter Lab. Starting with maybe the most exciting technology on the left-hand side, Ray, we use our Jupyter Lab to dispatch jobs to Ray. Our Jupyter Lab exists and interacts with, on the bottom left, an Apache Airflow instance, which helps us with our scheduling, and which also schedules the containerization of the lab. Our lab is able to dispatch complex, large-scale data workflow jobs to Slurm and receive back the engineering spec in a way that's parsable for both engineers and data scientists. Our lab is hosted in a Kubernetes cluster in AWS, and it is both able to design models for the Docker image hub of our Kubernetes instance and deploy models to topologies through Ray or Airflow. So when it comes to any kind of problem, the starting point is for the principals to have a meeting in the lab and to figure out what we need to expose to modify the system. And this gets us to my favorite slide, which is probably way too cute. When I originally saw Anyscale's branding of the Infinite laptop, I was extremely happy. My main practice in data science for the past 10 years has been helping Series A companies build research pipelines in machine learning with a consciousness of their eventual B round. So pipelines that are sufficiently advanced, sufficiently robust, and provide avenues for scaling. The idea of being able to hire junior data scientists in the early phases of a company, but follow a code pattern that will allow for first full-scale cluster deployment down the road, was to me first dangled by the wonderful technology DASC, which I have had a great relationship with. But it isn't until our current implementation of Ray in the Jupyter lab that I feel like I could actually sit down with a recently graduated data scientist and have them fairly rapidly designing models that would look like the first piece of code in this slide, which is unfortunately, all of the secret sauce is hidden, but it's one of our genome prediction models at Drift that parses, genomic data and attempts to understand either phenotype or patterns in evolution of phenotype. But as you can see, it's a standard 3-part pipeline of loading a data frame, pre-processing, generating, and creating the data object, and then training the model. Something that is pandas driven and very easy to step into for a novice practitioner. And then this second code cell illustrates how we would recurate the same model for ad hoc deployment from the lab into an arbitrarily scaled Ray cluster. So you'll see that there are two softwares working together in this process. There's Ray and then there's Airflow. And so the cell is curated at the top as a DAG. And so Airflow knows that it can grab this cell and send it out to our system. The particular functions are also decorated further as Ray tasks. And so when this code is pushed out to the cluster, Ray is able to pick them up and push them out to our AWS cluster. Down here, we have a little bit of curation of the Airflow DAGs. And in this instance, it's such a simple topology that these are just kind of placeholders. This certainly is a place where greater tools for teaching and understanding graph theory would help open up the problem space even further. But I feel fully confident with this pattern that our company is going to be able to sit down with not just junior data scientists, but potentially domain-specific experts who have an interest or an openness to working with code. We potentially can have people who used to run assembly jobs using a 100-person support staff running their own assembly tasks based on curiosity from their home couch. And it's just a very exciting thing. And I'm really honestly quite grateful to Ray for the technology. And then just to finish up, I'm going to share a sort of slightly more specific diagram of how the system works. And also wanted to say that internally we've been calling the system Falconer. And you'll have to forgive me for the poetry of that. In my youth, I trained as a falconer, and I thought that the relationship I had with my hawk was very special. The hawk is so specialized. It's so fast. It's so dangerous. It's such an elegant bird. And it sort of needs the falconer to guide it around the environment and set it up for the safest and most successful hunts. And so this topology here we're calling Falconer because on the left side we have our sort of Jupyter Lab Kubernetes Airflow Trinity. So this would be the area where we're authoring Docker images that would be potentially node components of executed topologies. And then we have a Ray cluster, which mediates our deployment of compute topologies for machine learning to AWS. So when Ray is asked to run a task, it 100% has a supply of curated data objects and specifically unit-tested Docker images that are able to process our data properly. And all Ray needs to worry about is executing a complex topology in the cloud, which it does so well. Just looping back real quick to the pain of bioinformatics. This is the kind of thing that we're talking about. We really want to separate the task difficulty of model curation and complex compute topology execution. And I think in this pairing of Astro and Way, we've really found great success at that. Um, anyway, thank you guys so much for having me here for this talk. It's really been so much fun sharing this with you. I hope more than anything that I have not stepped on the toes of any biologists or bioinformaticians. I've come to this project as a humble data scientist and have been lucky to be, learning from truly some of the greatest scientists in the world. And, I'm just really grateful to be speaking with you and to have had a chance to be contributing to the body of scientific research here. So, thank you guys so much. And I think that's it.